Hello, my name is Elisa Apsel. I'm a professor of electrical and computer engineering at Cornell, and I'm also a co-founder of flexible spectrum radio startup EchoICs. So I'm going to start by saying something that I think is uncontroversial. I think everyone in this room today is dependent on wireless connectivity. We've all become so dependent on having data anytime, anywhere, at the touch of our fingers, that when we don't have access to that data because of interference from other users or poor service, it can be extremely frustrating, or worse. If I'm a soldier in the field, it can mean the difference between life and death. And yet, as the number of users increases, maintaining that same level of service without some flexibility in our radio hardware is extremely difficult. But modern radios do not offer this level of flexibility. So how does EchoICs help that? So first, let's start talking about what radio is. So for those of you who are not familiar, the modern radio spectrum, the way radios work today, all of the standards that you're familiar with, things like Wi-Fi, Bluetooth, GPS, all of those things are allocated a narrow slice of the frequency spectrum. That frequency spectrum is almost completely allocated by FCC and other regulatory agencies to a range of commercial and defense applications. So what that means is that the radio spectrum is very crowded and almost completely allocated. So how do radios operate in this environment? So this is your crash course in electronics. The way that radios operate in that environment is that they are each allocated this narrow band of frequency, and they use very highly tuned electronics, circuits, that are tuned to only the frequency of operation of the standard that they are designed for. So for instance, a radio that is designed for, let's say, Wi-Fi 6 will pull out a signal at the frequency of Wi-Fi 6 from all the interference and noise in the environment, but it will only work for Wi-Fi 6. It will not work for GPS, it will not work for Bluetooth. So the alternative to this is something that has developed primarily for defense applications, is something called software-defined radio. And the way software-defined radio works is that it is, instead of using this narrowly tuned hardware, it uses broadly tuned electronics and pulls in everything, all of the noise, all the interference, all the junk, as well as the signal, and then uses software to pull out the frequency of interest. Okay, so the result of this is that you have a very flexible radio that is pretty inefficient, tends to be large, tends to be expensive. EchoICs offers the best of both worlds. So what we have developed is a flexible front-end radio, which is narrowly tuned, so that it offers the performance of conventional radios with the flexibility of a software-defined radio. So this means that we have a software configurable frequency selection, meaning that we can change the frequency of interest with a software configuration. We store and process only the desired frequencies, so we don't waste time, energy, resources on all the frequencies we're not interested in. This gives us a flexible, efficient, and small unit with 10 times better dynamic range, 10 times better signal-to-noise ratio, and some level of future-proofing so that changing standards can be adapted to with our radio. So the technology here is key, the way that this actually works. It's based on a technology that was developed in my lab at Cornell for a very tiny resonant element that can be reconfigured. So it's a tunable resonant element that's so tiny that it can be manufactured on a microchip. The best analogy to this, because I don't expect everyone to understand the electronics immediately, the best analogy to this is a guitar string, okay? So the way a guitar string works, for those of you who are familiar with it, is you strum a guitar string, you can change the effective frequency of the tone that propagates on that guitar string by changing where you press that string to a fret. So you change the effective length of the guitar string, it changes the wavelength, it changes the frequency, okay? We do the same thing with an electromagnetic wave on a chip. Okay, so we use something called a transmission line, and we change the effective length of this transmission line using switches that are embedded underneath the transmission line, which can then short that transmission line to ground effectively pressing the string to the fret, okay? And that gives you a change in the effective wavelength. We can use this element to build a range of transceiver circuits, radio circuits, to build a tunable radio. This is particularly salient in defense applications. So in defense applications, as Colonel Winterly says here, they operate in an evolving threat-based environment, which requires flexibility in the radio. And EchoIC's solution offers a radio that has 3 times better battery lifetime at half the weight. As a result, our first customers that we've been talking to a range of potential customers, and the first customers that we have identified are in this defense market. Our first target customer that we are talking to currently, we believe we can provide up to about 10,000 units per year with about $2 million of annual recurring revenue at good margin. The depth of this market, however, is deeper than this. If we look at North America alone, the depth of the software-defined radio market is about $8 billion. Globally, it's about $16 billion. But as long as we can develop this product and reduce the cost, this opens up also the global IoT market, because the IoT market also wants flexible radios that can accommodate multiple standards, but it is a much more cost-sensitive market, so we have not targeted it as our initial play. But it is quite a large market. So where we are now, in 2021, we developed the basic technology and filed IP. In 2022, we have developed a demo chip design and done a market analysis, I-Corp, that was NSF funded. In 2023, we are building a transceiver prototype chip, and we are currently in the process of completing the design and testing of demo boards that enable transceiver testing from 2 to 8 gigahertz, and as well as transceiver data sheets. In 2024, we plan to be able to provide demo boards to customers, as well as fabricate a second-generation chip and ship first product. And finally, in 2025, we hope to scale production, have our first full product, and be able to deliver tunable transceiver IP to customers. Currently, right now, we are seeking connections to radio integrators for anyone who wants to help us with that, as well as some additional funding. So while I'm here today, my co-founders, Leica Nafuye and Tom Tapin, are busy actually developing these demo boards to deliver to customers. This work, most of the concept for this was developed as part of Tom Tapin's PhD thesis. So he has about a decade of experience in RFIC design. Leica Nafuye has been working on the digital backend as well as the frequency synthesis blocks. So he also has about a decade of experience in IC design. And while the two of them would be happy to be here today, they're too busy pushing technology boundaries. So with that, I will open up to questions.
Hi, super cool. So I'm not sure I understand the business. Are you licensing technology, selling chips, selling radios? What's the business?
Excellent question. We could do all three. Initially, what we're thinking, so our first play, we've done some market analysis in order to figure out where the easiest sort of minimum viable product space would be. And what we found is that it looks like the defense space is our minimum viable product. The customers in the defense space want a chip. They don't necessarily want the IP. They want us to provide a chip, and then they want to integrate that chip within a handset, right? So that's our first play. That's where we see ourselves going initially. Long term, this idea of silicon IP is potentially attractive, but I think that that is not where the defense market is primarily situated right now.
Yeah, could you just talk a bit about, even with the defense use case that you're talking about, can you explain, just building on his question about the business model, like, so when you talk about $2 million in revenue, in recurring revenue, so can you just explain the unit economics, like how are you charging per?
Right, so we're basically doing a comparison to, there is an existing product on the market that is pretty inefficient, pretty low performance. It's by a little known company called Analog Devices. You've probably heard of it. It's called the 6391. This is the sort of the workhorse part on the market, because in electronics they name things sexy names like 6391. And that is approximately $200 to $250 a chip.
Yeah.
That's basically what they sell it for. So we're assuming what we're trying to do right now is build a drop-in replacement for this that has much better performance, much better energy efficiency, has much greater flexibility, and could cost about the same.
But it's one time. It's not recurring. Is that fair? Is that or?
It would be recurring because, so for instance, that part has been around forever, and they do not have to redesign it because it is a flexible radio. And that's kind of the benefit of building a flexible radio, is that we don't have to necessarily redesign it every so often. I mean, probably you have to do it every so many years, but it's not an annual redesign. So that is recurring revenue.
It's not recurring in the SaaS sense.
Okay.
It's just recurring that you're going to
It's
sell
like
a lot of
repeating
Yes.
replacement, like razor, like just repeating.
Yes.
Super. Okay, thank you very much.
Okay.